But before that, we have some announcements to be made. And the first one is join my GB. Apps are out now. They're due in about a week or so. You and I led one last year. It was so fun that we're back again. So join anyone's GB really. It will be a lot of fun.
In the most recent announcement, we have posted a link to the announcement that contains the GB form.
Second thing is Lab 1 was due already, and a lot of you have not done it, but that's okay. Everyone has midterms. But Lab 2 is still being dropped tomorrow, and you will have a little under 3 weeks to finish it, so lots of time. Additionally, if you've not finished Lab 1, or you want to get started on Lab 2, which is good for you, then we have a work session this Sunday, 3 to 7 p.m. So come by, we'll have snacks, and we'll be there the whole time to answer any questions that you might have. So this is a really good time to get ahead on your labs, and we'll be there. Maybe hard, who knows. And I think finally, we have several documents that are helpful for all of your assignments, and these are like Verilog, basics, and then a frequently asked questions document. So these will all be linked in every lab spec, and if you are stuck on like syntax issues or you like, have consulted the channel and it's not there yet, make sure that you check the frequently asked questions before asking it. If it's answered there, great. If not, then we'll add it to the document. So you guys are helping us create that documentation. So, is everyone good so far? Alright, so far you hopefully know these concepts, logic gates, binary and arithmetic and logical operators, because hopefully you have taken M51A. If you haven't, hopefully you know these anyways. But they'll be important for this lecture. So I'm going to propose to you a problem that you might not know how to solve in Verilog yet, but by the end of today, you will. So consider this. I was a freshman 2 years ago. I lived in Rebirth Hall, 4-5 North, and my neighbor was a biz econ major who had a very interesting schedule that did not match with mine. And so as a result, it was not a good time. So suppose I want to make a circuit describing him. So I can call the RAs on him in advance because that's what the situation deserves. So in this case, each of his actions depended on previous actions, but because we're just dealing with combinational logic so far, how do we know what previous actions there were? We can't do that yet, but we will learn how to do that in a little bit. This is how I felt living next to that biz econ major. I think it's a pretty accurate representation. Okay, to make this annoying neighbor circuit, we'll need a couple things. So we need to actually have memory now, because we need to remember what state or what action came before. What was he doing, and what will the next state be? Those will depend on each other. Then we'll need clocks, so we can update these memories synchronously. And finally, how do we know what action goes to what action? Let's say he was asleep, and where will he go next? We don't know. So now we need to define some conditions to say, oh, he was asleep, but now he's woken up. What is my annoying ass neighbor going to do? So we will need to define these transitions, and we'll see.
Cool. So first we're going to talk about the, essential part of this annoying neighbor circuit, which is how do we remember or keep track of the annoying neighbor's current activities? Like, so far we've done a lot of combinational logic, which is where your output is directly determined from the inputs that you supply. But if we stop supplying those inputs, the output goes away. We want a way to make it so that we can keep remembering, we can keep the output even when the inputs are no longer being supplied. I will take the mouse. Thank you. So we're going to start with a very basic circuit that's not actually going to be our memory unit, but it's going to serve as sort of a foundation for it. This is what we call the D latch, or D stands for data. Basically, in this circuit, when the enable line is high, then the output Q will be the value of D. And when enable is low, even if our D value changes, the value of Q will just be whatever D was before the enable was turned off. So what this means is that as a result of turning off our E input, we can actually force our circuit to remember what D was before the enable changed. This is really important because this is like the first stepping stone into understanding how memory works in hardware. However, there are a few problems with this sort of idea. The main thing is that a signal like D, like an input signal that we want to remember, it's not necessarily like a perfect signal. There will often be like random fluctuations, and if this happens, we need a way to make sure our memory is sort of resilient to those sort of random fluctuations. As we can see in this diagram, we have a D line that sort of is mostly high, and indeed the input that we are trying to supply is an entirely high, like it's a 1 basically that we're trying to pass in as our input. When enable is turned on, we are able to record that value, but due to this one random fluctuation right at the end of our enable signal, like when the enable turns off, the output of our latch, as a result, it gets turned off and doesn't recover. Because all the latch sees is, oh, when the enable went down, D was low, even though this was actually a random fluctuation and not meant to be the intent of our circuit's behavior. So this is, of course, rare, but it highlights a problem with our memory cells so far, and it's really one that we need to try and solve. This latches value can change whenever the enable is high, and this is a behavior known as level triggering, because the latches value can change based on the level of the enable line. Level triggered memory cells are volatile. If our D value is unpredictable, the latch output will also be unpredictable. We want our cells to be predictable and stable, which means that even if our D is an unstable input, our latches value should be very stable and consistent. So the question now is, how do we do that? Is everyone following along so far? Basically, the idea that some geniuses had back in the early days of hardware was, instead of updating the memory whenever the enable signal is high and just doing that on the level of the enable, we do it at the exact instant that the enable sort of goes from low to high, which is known as the edge of the enable line. This is therefore known as edge triggering. It's when your enable value changes, so when it goes from negative to positive, then that's the positive edge, and when it goes from 1 to 0, that's the negative edge.
Sparks, you just have a question?
Oh, yeah. So for D, that would be a signal that we're getting.
Yeah.
But for the enable and the latch, are those also signals, or are they states that our circuit can be in?
So the enable is a signal that we're going to get from somewhere, and we'll talk about how exactly we're going to get this enable signal in a little bit.
Okay.
But the D is an input that we're
Yeah.
trying to basically remember in our circuit.
Yeah.
And yeah.
And the latch is also.
And the latch is actually within our circuit. It's the output from the circuit that we're trying to build.
Oh, okay, I see.
So as we can see,
Could you go back to the
this one.
Yeah, sorry.
So as we can see in this diagram, we have an enable line, and this time instead of changing our output on our latch every time whenever the enable is high, which would have resulted in it going up and down a couple times because of those fluctuations, we can see that it only records the latch value at the instant that the enable line goes from low to high. And this is in the intended behavior because it means that our latch output is stable even though D is not entirely perfect. Jerry?
Does it also update when it goes from 1 to 0?
It can. It depends on the behavior that we configure our circuit to have. Any other questions? Oh.
But this doesn't solve the problem if it was unstable during the edge, right?
Correct. We'll talk about that in a little bit, but this is sort of a getting started kind of thing, where we've eliminated most of the instabilities so far. There's one that we still could have, but we'll get to that soon. So in order to accomplish this edge triggering behavior, what we actually have to do is we take two latches and we chain them together. So what this is a rather complicated circuit that you can trace through on your own time if you are so inclined. But basically what this is doing is that the output latch, which is the Q over there, will receive the last value of this latch before the enable changes. So this the enable being high will cause this latch to constantly be recording the value and that one to not be. And then when enable goes from high to low or low to high, it's going to swap them, and that enable will record this value, but this value will no longer change. And the result of that is the output latch will be stable and change only on the edge of our enable line. Does that make sense to everyone? Are you fair?
So just to make sure, so you're temporarily storing the data line?
Yep. That's basically what we're doing here. This latch temporarily, like basically the first latch is going to constantly be recording the data line, and then when the enable flips, it'll stop recording the data line, so it becomes constant. And then the next latch will receive a value at that point, because the next latch is turned on to constantly record whatever its input is. So since only one of these is like enabled at a time, the result is that whenever the clock goes from high to low, there's a brief moment where the value gets propagated through. Sorry.
So then the latch of the first one becomes the data line for the second one?
Yep.
Okay.
Yeah, that's what this wire right here is indicating. Yeah.
How come we don't use stabilize the enable?
We will be. That comes next.
Jerry?
If Q's the latch value, what's Q prime?
Just the opposite of it. It's just a convention that when we're drawing circuits for like latches, flip-flops, etc., we have both a Q and a Q prime output. And the Q is the actual value of our data, and Q prime is the opposite of it, like the complement. Questions? Cool. So this device, as I just said, it's called a flip-flop. And it can store 1 bit, and this is the block diagram for it, where basically we have 2 latches, there's an enable, and the configuration of these NOT gates will determine, like basically whether there's 1 NOT gate here or not, will determine whether this is a positive edge triggered flip-flop or a negative edge triggered flip-flop. So, of course, the problem with this is we can only store 1 bit per like flip-flop, and if we want to store, like, if we want to do anything with an actual like circuit that actually takes in useful data, we probably want more than 1 bit in memory. Like, as you guys would have noticed when doing your ALU, the actual like circuits that we were using, that we're building, they took 4-bit inputs, which is already more than this flip-flop can handle. So in order to store more bits, we basically have to chain multiple flip-flops together using something called a register. So basically what's happening here is the clock line, which we'll talk about what clocks are in more detail in a little bit, but this is basically acting as an enable for all of these flip-flops at the same time. So the result is if we have an input that's multiple bits, each one gets its own flip-flop, the clock will trigger all of these flip-flops at the same time to store the value of the input, and it ensures that our flip-flop values of all 3 like bits are synchronized, so they always get updated at the same time. Which means that if we pass in a new 3-bit input, then it will be stored as an entire 3-bit like sequence in these flip-flops, and the output will be stable and accurate to what the inputs were. Does that make sense to everyone? Cool. So, next we're going to actually talk about clocks. So, as we said earlier, we want our reads to be predictable and stable. So we need a way to ensure that when we're enabled, like in addition to just making sure that we eliminate the instability with the like input data, we have to make sure that the times at which we update our memory are predictable and like not just subject to random fluctuations in an enable line. So the way we do that is with a clock. Basically, if we attach the enable input of our register to a clock, we can synchronize our memory. And I know I've just been throwing around the word clock a lot, so we're actually going to talk about what that is now. Basically, this is what a clock is in hardware. It's going to be a 1-bit input that just toggles between 0 and 1 at a very specific defined frequency. So our FPGAs, the DE10 lights, they give us 3 clocks that we can work with. There's 2 that are 50 megahertz and 1 that's 10 megahertz. If you're not familiar with what a megahertz is, this is basically what that is. So every clock has a period, a frequency, and a duty cycle. The period is the time that it takes for our clock to complete 1 full cycle from one positive edge to the next. If you guys are familiar with like sine waves, like if you were in 102 or something like that, you would have heard the terms period and frequency already. The frequency is going to be the number of cycles per 1 unit of time. So frequency of 50 megahertz suggests 50 million clock cycles per second. Frequency of 1 hertz would be 1 clock cycle per second. And the duty cycle of the clock is the percentage of time in each cycle that it's going to be high. So in this case, you can see we have a 50% duty cycle because for half of each period, our clock is high and the other half is low. And this is the clock with a 2 hertz frequency because every second has 2 of the periods in it. Does that make sense? Can everyone see why we use clocks to actually synchronize our memory cells now? Cool. So sometimes we don't actually want 50 million clock cycles per second. And if you take the example of, say, a stopwatch, which you actually will be taking this example in your next lab. If we want a stopwatch that updates its counter every millisecond, we can't really synchronize our updates to a 50 million clock cycles per second clock because then it's not going to be accurate to a millisecond. It's going to be updating way faster than that. So this would be way too fast, so what we need is a way to actually slow down our clocks to perform various purposes. And if you are familiar with like the concept of frames per second in a video, this is also something that you'll learn throughout this year. This is the frame rate of a display, like the refresh rate or the frame rate of a video. These are all things that are very intrinsically linked to the concept of a clock. So the solution is basically to design a circuit that divides the clock frequency, so our edges occur at a slower rate. What we can basically do is we count the positive edges of our clock, and every time we want to flip our new clock, we do so based on a certain threshold that we've decided. So as we can see here, we have a clock that's 1/4 the pace, 1/4 the frequency of the original, or actually that's 1/8 the frequency of the original. It's 1 duty cycle per, or 1 period per 8 periods of here. Wait, I count? Yeah, 8. It's 1/8 the frequency of the original. We're toggling this every time our counter counts 4 clock cycles for a total of 8 per period. Does this make sense to everyone? Cool. Now we're going to design this clock divider in hardware, and by we I mean one of you. Who would like to volunteer? Sparsh, come on up. So these are the parts that you'll need when designing a clock divider. Oh, Jerry.
What's the equals equals?
The equals is a comparator, but basically it's gonna take 2 inputs and spit out whether or not they're equal. So, yeah, put the screen up. There's already markers here. Lovely.
Well, do they work? Do they work?
We'll find out. I have markers in my backpack too. But yeah, basically in this clock divider, you have an adder to increment some sort of counter. You have a register for the sake of storing like some sort of value. You have the comparator that tells you if your 2 inputs are equal. You have a mux, and you have a flip-flop at the end. And now it is your task to piece together the parts and determine how exactly we're going to do that. So as a motivational stock image told us, don't watch the clock. Do what it does. Keep going. That's what Sparsh is going to do right now.
Okay.
You have the parts that you need right here.
You can
We
also
will-
look over there.
You can also
Okay.
look at that too. Marks might be easier.
Okay. Wait, which was the initial clock?
The initial clock, you just draw that input.
Oh, okay.
Or you can even draw inputs for you. Oh wow, okay, that is a very old marker. Does that one work? Oh,
Okay.
lovely, okay. You get that.
Put it into the register. Or not, or to implement the register. Add.
I would recommend drawing them as like the blocks that are
Oh,
actually there, because
okay,
you can
okay.
see what the inputs and outputs are of each of these blocks.
Okay.
Right,
How many bits does the register have?
The register, it doesn't matter. I mean, it does matter, but like in this case, we're doing a very abstract drawing of a clock divider, so you can just assign a number.
Wait, what's the DF app?
The default clock.
What does
That's
max
the
mean?
that's the memory
It
unit.
takes two inputs
Oh,
and then
okay.
determines an output based on what the two bits are, or multiple.
Okay.
And in case you guys aren't aware, the little triangle notation at the bottom of the block basically indicates that that's where a clock input goes.
Or any label in general, but it's a clock for our cases.
Yeah.
Do we have the recipe? Yeah.
This goes to. Register.
Oh, what's up?
It doesn't matter. Again, this is a very abstract sort of clock divider that we're making. So, in actual hardware, when you're designing, when you guys are writing the clock divider in Verilog, you will actually have to specify numbers of bits. But for now, we're just drawing a sort of generic structure for what it will look like. Would you like to explain what's going on here?
So I'm not quite sure, but my idea was that if the clock comes in, you put it in the memory, or sorry, the memory. Then you.
Well, we have two different ways of storing things here. We have the register for like larger numbers, and the DFF is just like one
Oh, I see.
bit.
So in that case, you would increment the DFF, and then you add up the you add in the adder, and then from there you see if that would be equal to the value in the big register. Perhaps, and if the value is equal, then you would follow it.
I think conceptually you have the right idea, but we will explain.
Right, thank you for
Yes.
volunteering.
Thank you for volunteering. No, I want to draw it.
Oh, do you want to draw it?
What if you close my computer so they can just see the whiteboard? Without,
With that,
actually, no, it's fine. Can you guys see things that we draw on the whiteboard?
Yeah, yeah.
Okay.
it also says
Oh yeah, you could do that. We just do that.
oh.
That. There.
There we go.
Chill.
Got it.
Cool. So we're going to start with a clock input. And basically the idea here is we need to first of all figure out how we're going to count up for our clock divider. Because as we established, we want our clock divider to be based on a counter that tells us when to flip the clock. So in order to do that, what we can do is we have our register store the register stores the the counter value. So like some number that can be from 0 to some large number depending on how much we want to divide our clock by. And we will enable this register to change its value every time our clock pulses. Now the actual new value of the register will be dependent on our adder, right? Because we want it to increment by 1 on every clock edge. So we have an adder. And an adder is a combinational module, as you guys know. So this will take in as input the register, and the other input would just be 1 to increment it by 1, right? And the output of this will go back into our register, or not quite, because when we need to reset the counter, we also need to reset. We need to make sure that this is 0 and not the adder increment. Oh, Jonathan?
Can we rely on bit overflows to just have it reset when it runs out of space, or?
You can if you want to divide your clock by a factor of 2. But for example, if you want to have your clock be like 1/5 the frequency of the original, you can no longer use a bit overflow. But yes, in theory you could. It depends on the frequency that you're trying to produce. So in this case, I'm gonna move this down so there's more space. In this case, what we need is the input of this register should be a mux, where basically we're going to be picking either this input or the number 0. And I'll give myself way more space. And the thing that determines the whether or not we reset this register is going to be based on whether our counter value is equal to some sort of predetermined threshold. So this is our counter value. This is our little comparator thingy. So now this is our counter, basically. When on every single time this clock goes high, this value will be updated either with the number, the counter +1, or with the number 0, depending on this equality comparator thing telling us whether this number is already equal to the threshold. If it's equal to the threshold, this is going to be 1, so it'll select the 0 input. And if it's not equal, this output will be 0, so it'll select the incremented value. And this is how we get it to basically count up clock edges. Does this part make sense so far?
What about the flip-flop? You didn't use that.
Correct, we're gonna use that next. So basically, once we have done this counting, we need to actually flip a new clock, right? Which means this new clock is gonna be a separate sort of memory cell that retains its old value even when this counter changes. So what this new flip-flop is going to be, gonna go right here, and it's going to basically be clocked by our original clock. And does anyone have an idea what the input to this flip-flop is going to be? So the input to this,
Well, it could be like all of, well, like it could compare like other, like the value in the register is equal to some sort of like it's equal to like 0 or something. Something that will just happen once every like few clock cycles.
it could, it doesn't need to.
Could you use the output of the equals block?
For what, for the input here, the clock?
For the input.
You could, but keep in mind, what we're trying to do is make it so that this D flip-flop,
Yeah.
on every clock edge, it's updated to what we want our new clock to be. So this could either be the original clock value, or it can be the flipped version.
So can we connect the clock to it again? If it goes to what we want the clock value to be?
Well, yes, but we have to actually flip it. So I'll give myself a little bit more space, and then there's a number of ways you can do this, of course. But what Claire and I were thinking when we designed this clock divider was you basically just feed the old clock back into itself with a NOT gate, and this will allow you to basically when this D flip-flop needs to be flipped, it'll get flipped. And therefore, if we do it this way, if we do it with where we flip it on every, where we flip its value on every clock edge, we actually need to change this to make sure that we're only updating this on when the clock is supposed to be flipped. So we can actually erase this. And as the clock input to this D flip-flop, if we were to do it this way, does anyone have any ideas what it might be? JC?
Question. How do you know the initial condition of the flip-flop?
Well, in this abstract example, we're not specifying it, but in hardware, there are ways to specify initial values to registers, like when we're writing Verilog. not for the purposes of a clock divider. In general, yes, but like our clock divider will produce a new clock at the same frequency, even if it starts at 1 or 0. John,
Oh, for the input as the clock, would it be the output of the equal?
yes, yeah, we can do it that way. And then so this works because this will only go, this will only have an edge from low to high, as in it'll go from 0 to 1 whenever the threshold is met. So whenever it goes from, like, whenever the threshold is equal to the counter value, this goes to 1 for 1 clock cycle, and it will trigger an positive edge that will cause this to flip. And this is our output clock. Yeah, that's basically it. Oh, Sparsh.
What are the two arguments for the equals in this, for the equals gate in the diagram?
So
One is the
basically,
threshold, and then
one of the arguments is the threshold, which is, as we showed in the previous slide, we have a set value that determines what frequency we want our new clock to run at. So the threshold is like, say if the threshold were 4, then our new clock would be at like 1/8 the original frequency.
Yeah.
Claire, do you want to put the screen down and we can show them the actual solution?
Prem?
Yeah.
Just to make sure I'm understanding this right, so what the multiplexer is doing is it's saying that if the threshold equals whatever has just come out of the register, then the multiplexer is like, I guess, it'll output whatever the result of the one bit was. In that case, it was 0, so
Yeah.
it resets the register. And if it's not, then it'll just put the part from the line above. I don't remember what it was, but it was just the value of the register at that time.
Yeah. Okay,
So
what was
so
the
like,
correct. That's a great question.
Always say no.
Well, yeah, but how do we say no? We don't know where the buttons are.
Left, right to select, and that arrow thing to execute.
There are no such
Oh, there we
arrows.
go, it's gone.
Oh, it's not. Okay, lovely. Anyway, back to here. Adrian, sorry.
Yeah.
Repeat the
Yeah,
latter
yeah.
half of your question.
so like if the threshold was equal to whatever has just come out of the register, then you reset the register to have 0. And if it's not, then it'll just increment. It'll take the incremented value of the register and just replace that value back into the register.
Yes.
Is that okay?
In the design that I showed earlier, that is what we did.
Okay.
It would seem that when I made this lecture, like 6-7 months ago, we designed this slightly differently. So we'll also walk you through this design right here. Basically, what this is doing is we have an adder that's adding 1 to the register output, and it's updating the counter on every single clock cycle. So we're actually not doing the like based on threshold resetting it here in this adder, because I guess in the clock that we were designing originally, we could rely on integer overflow, which is what Jonathan said. So in this design, we actually do entirely just rely on integer overflow and flip the bits of the and like reset the counter that way. In this section, we have the actual like new clock, which is being reset, and what we actually use the multiplexer for here is we either set the new clock to be the original clock or the flipped version based on whether or not the counter is equal to a threshold. As you can see, this design also works, and it basically uses the same components as the original. It's just slightly more simplified.
And the threshold was 0 because you're relying on overflow?
In this case, yeah, there's no threshold
Okay.
because we're relying on overflow.
Okay.
So we're just saying whenever the clock thing goes back to 0, then reset it.
Okay.
What do the slashes mean in the out in the
So basically, in a lot of circuit schematics, if you see slashes, it usually indicates that the output or like that particular wire consists of multiple bits, which we specified here because the output of this adder could be multiple bits, and likewise for the register output and input. So those particular segments are multiple bits. Does this design make sense to everyone? Does the design I showed on the board also make sense to everyone? These slides will be posted afterwards as well, and we will have you guys design a clock divider, so if you have more questions, you'll be able to ask us then. Anyway, so in Verilog, we have to actually figure out a way to do that, and this is where the writing code part comes in. But basically, Verilog has an always block construct that we've talked about only in the context of combinational logic, we have the always comb construct that you guys use to make your mini ALUs. In sequential logic, where we have to actually rely on a clock, we can use this more generalized form, which looks like this, always at and then pause edge clock, which basically, if you couldn't already guess, it runs the always block whenever there's a pause edge on the clock line. You can see with this handy graphic that Claire made that basically it turns yellow whenever the clock goes, whenever it's supposed to be triggered. So the first one turns yellow whenever the clock has a positive edge, the second one turns yellow whenever there's a negative edge, and the last one, it just turns yellow anytime clock changes. The contents inside this parentheses are what's called a sensitivity list, which basically, it's saying that the always block is sensitive to changes in those particular ports. Does this make sense to everyone? Justin?
Wait, sorry. I didn't quite follow that. So like, is it like a 3-line statement?
No, this is a 1-line statement. It's basically like, this would replace always comb if you, have you gotten through that part of the lab?
No.
Okay, well basically, when you do the lab, you will see that we use an always comb construct, which is short for always combinational. And this block runs anytime you change anything in your circuit. Like anytime any of the inputs to a combinational block change, the output will be updated to reflect that, because that's how combinational circuits work. If we want to do this where you only change things or you only like affect your circuit whenever a clock is updated, then we have to use this more fancy always at syntax, which is basically saying always run this block at a change to the clock or at a positive edge to the clock or something like that.
How is that? How are the 3 always? Are those like parentheses like actual? Is that actual?
This is actual code, yes.
Okay.
These are these 3 lines are not. You won't use all 3 of them at the same time. These are just 3 different ways of writing an always block that will trigger when your clock changes in a certain way. Jared.
Could you replace clock with any variable or any
You could.
input?
However, I would warn you against doing that, because if your input clock is not synchronized, then like if the thing that you supply to this always at sensitivity list thing, if it's not synchronized to a clock, then the Quartus compiler will synthesize this in hardware to a latch. And as we've talked about earlier, latches are really bad and unstable. So this was actually a trap that many teams, including us, fell into last year, where we tried triggering an always block with a button press. This causes very undefined and very unwanted behavior. So in general, you will always be using clocks to trigger your always blocks. And that's basically non-negotiable. Any other questions? Does everything we've talked, oh, Justin.
So would the sensitivity lists just follow that little bit of code?
The sensitivity list is the stuff in between the parentheses. It's saying that the block that will follow this line is going to be sensitive to the changes to the clock.
Okay.
And you don't really need to worry about the code. We have syntax examples in our Verilog docs as well, if you need more concrete explanations. This is just so you guys can see like a visual of how it runs a block, an always block. Jerry.
Does this mean Quartus will synthesize an always comb as a latch?
No, because Quartus is smart enough to figure out that if you specify always comb, you're trying to make an actual combinational circuit. So it will actually create a combinational circuit with just wires and gates and how it's supposed to be. Sorry,
wait, can you explain again why is it like so bad to like, so you said you had like always add to like a button?
Yeah, so remember earlier in the lecture we talked about latches?
Yeah.
Do you remember why we didn't want latches and why we tried to design a flip-flop instead? The idea is basically that a latch is basically designed to produce an output that's not as stable, because it can change anytime the input changes over a much longer period of time. So if you have your latch triggered on like the level of an enable line, for example, then anytime your input fluctuates within the period that that enable is high, then your latch will also change. And generally what we want is that we want our memory cell to be resistant to these sorts of random fluctuations. So if we have our circuit triggered on a button press, then Quartus will synthesize this to a latch, which means it's a little bit less stable. And anytime the button press, like anytime the button edge, even if you specify like pause edge button, it's not gonna really know that this is something that it can rely on as having consistent and well-defined edge. So it's just going to synthesize it to a latch, and this can cause all sorts of undefined behavior in hardware. Any other questions? Is everyone following what we've been talking about so far with respect to clock dividers, memory in general, etc.? This is all really important for Lab 2.
So, for the memory, what you're saying is that the value in memory is a signal, and the value of the signal is dependent on what the clock is doing?
Yeah, basically. The the input to our memory cell is some sort of signal. Inside the memory cell, it's basically like a, the circuit is basically, as you saw earlier, it's like a feedback loop between a couple gates that enables it to keep that value over an extended period of time. The actual implementation is a little bit more complicated, of course, but we're not here to talk about that. But basically the enable line, which is in this case is a clock, and in most cases should be a clock, is a line that essentially tells your memory when it's allowed to update itself to whatever the current input is. JC?
Could you still use a clock to implement combinational logic?
Well, it wouldn't be combinational at that point.
Okay.
The idea being that if you're only updating a memory cell like every once in a while, there has to be some point in which it's not being updated, which means it has to remember its previous value. Like the value from 1 billionth of a second ago. And if it's not updating instantly according to the inputs, then it's no longer combinational logic. That's just how it works. Does that make sense?
I mean, what if you like put every thing you want to keep track of like in a register? I mean, you just say your program runs at like rate of whatever your clock is.
Yeah, so the moment you introduce registers or memory into a system, it no longer becomes a combinational system. A combinational circuit is one that operates without any sort of memory. It entirely operates based on the current inputs and what their values are. So if you introduce some sort of memory to remember those inputs, then it's a sequential circuit. Does that make sense?
Yeah.
Adrian?
So would you have to use like an always comb block if you wanted to implement like a design that had that changes based on the value of like a button or a switch or something?
No. What you would do is you would use an like sequential block, and you would read the value of the button on the clock edge.
Okay.
And store that in a register.
I see. Okay.
Would it be correct to say that you'd want the duty cycle to be like as close to 0 as possible so that you can change the value as infrequent?
No, because Claire, you'd like to answer this one.
No, because again, we want to have some level of stability, and not only that, but as we'll cover later, a lot of the things that you want to attach to the clock, so we're going to use a buzzer in lab 2, etc., actually want a 50% duty cycle to work. So, do you have anything to add to that?
I was just gonna say, like, the fact that we're using the edge of the clock already means it's like changes are occurring at an instantaneous point in time rather than at a like small duration. It's like, or like basically instantaneous. The time it takes for a clock to go from low to high is negligible in the context of a digital circuit or an FPGA. So the fact that we're using the edge means it's perfectly fine to just use a 50% duty cycle. And in fact, if you use a duty cycle that's super close to 0, it may start treating those ups and downs like fluctuations, or it might not read the edge properly.
Oh, I see. Oh, so what you're concerned about is how often you have the switch from up to down, not like whether you're 0 or 1, but like
Exactly. And how often we go from 0 to 1 is what is basically our frequency.
Okay.
How often we go from 0 to 1 per second.
Okay, I see.
Any other questions? These are all fantastic questions. Thank you guys for asking them. All right. Hello. Oh. Where did my cursor go? Oh, there it is. Okay. One last topic with respect to all of this, clocks, registers, etc., and then we will move on to probably what I think is more interesting stuff. Anyway, so previously in combinational logic, we used the equals operator, which you probably didn't think about because frankly the equals operator is just the assignment operator in like any programming language. But this in Verilog is known as a blocking assignment. This basically means that when you write a always comb code, then it's going to execute those one at a time, But in the context of hardware, it means that all of these happen these happen in sequence, but since they're all instantaneous, it doesn't matter. It's equivalent to basically creating a combinational circuit. However, now that we're doing sequential logic, we have to use something called a non-blocking assignment, which basically what this means is that instead of waiting for every single calculation to finish before doing the next one, we just tell Verilog, we want you to do all of these assignments at the same exact time. And the reason for this is because if we use a blocking assignment for a sequential block, let me check, did I use the slide? Yeah, okay. So the reason for the reason for this is because since we expect all actions in a sequential block to occur at the clock edge, if we were to tell the compiler to block the assignment based on the previous ones, it could introduce some sort of unwanted delays, and suddenly, as you can see down here, some of these assignments are no longer occurring on the clock edge, which is bad. So what we use is a non-blocking assignment to tell it to all happen on the clock edge simultaneously. The result, of course, is that if you're trying to update something and then use its value to update another thing, you can't do that in sequential logic. You have to wait till the next clock edge before you can use that value again. And there are workarounds for this and more as far as advanced computer architecture topics go with respect to basically having a value somewhere and then reading it directly from the original source, but we're not going to talk about all of those. So the rule of thumb you should be aware of is use blocking assignment, which is the equal sign, in combinational blocks, and use the non-blocking assignment, which is the less than equal sign, in sequential blocks. Justin?
Is it possible to do a non-blocking assignment in a combinational circuit?
It is possible. I don't think it makes a difference, does it? Yeah. I'm not entirely sure, but my gut tells me that it would not make a difference.
So, but is it like the thing where, as with normal coding language, where you go from top down to bottom, and if you said A equals B, B equals C, then at the very end C would equal A. But if you use a non-blocking assignment, then you have no guarantee of which one happens first.
Correct.
Okay, so that's why you probably should use the blocking assignment in a combinational circuit.
Yep. That's exactly it. In a combinational circuit, the order, since they're all happening instantaneously, we can tell Verilog that we want to preserve this sort of order. But also, in general, you should not rely on the order of your combinational lines, because in hardware, that order might not be preserved. The blocking assignment is more of a convention thing than it is actually telling your hardware that you want to do certain assignments in order. So in general, when you're writing code for a combinational circuit, you should be operating under the assumption that in real hardware, you're not going to be able to guarantee a specific order of things, and you should be sort of designing your circuit to mitigate that need. Any other questions? Jerry?
Wait, if you go back to the
one?
yeah. How does the blocking work on the left diagram?
It would cause undesirable behavior.
No, if you set A equals in, does B get connected to in after, or because they're all connected, right?
Yeah, I think what would end up happening is B gets connected to in, and C gets connected to in as a result. But since you're doing this in a sequential block, this just introduces delays that cause your values to no longer be stable. And we'll talk about exactly what unstable values means, or Claire will, in 2 minutes. Right?
Oh, well, right now.
Yeah, well, right now. Does anyone else have any questions? Oh, Kevin.
Could you, for the previous slide, could you explain what the non-blocking code does?
This one?
Yeah.
So yeah, this code basically, you have 3 registers, A, B, and C, and on every clock edge, A takes the value of in, B takes the value of A from before it was assigned, and C takes the value of B from before it was assigned. So the end result is you can see this lovely diagram that Claire and I made, where basically in is getting passed here, and it's gonna get, A is gonna get updated here, and B is gonna get updated here, and it's just sort of passing them along on every clock cycle. So you pass it in here, and 2 clock cycles later, it ends up at the end.
Okay.
Does that make sense?
Yeah.
Any other questions?
Wait, so the blocking one's the one on the right?
The blocking one is the one on the right, and it looks a little funky because frankly it is a little funky.
Okay, but the non-blocking like assignment operator is the one above it. Is
Uh,
that like the less than equal?
Yeah, the less than equal is the non-blocking assignment operator, which is confusing because the less than equal is also the less than equal in Verilog. It just, depending on where you use it, like if you use it in a condition versus in an assignment statement like that one, it will interpret correctly. You see?
So on the left, if A and B are like opposite, will your hardware like yell at you, or does it just die? Or, I mean,
I have no idea, frankly. That we could figure that out. Like, yeah, we could actually show you how to figure that out at some point because Questa gives us the ability to look at the schematic for a circuit that we describe in Verilog. So, yeah, we could take a look at that. That seems like it would be interesting. Sorish.
Wait, so the code on the right is the non-blocking?
The code on the right is the one that we want to do. Yes,
Yeah,
non-blocking.
So non-blocking. Okay, so if they all happen at the same time, and like let's say like C getting set equal to B happens at the same time, B gets set equal to A, then does C get like what does it end up get, like does C?
C will get the value of B from before B gets written to the value of A. Usually how this works, like way under the hood, is that the reads all happen first and then the writes all happen.
Okay.
But like you don't really need to worry about that detail. You should just know that C gets the value of B from before the clock edge. Sparsh.
So is it like executing these lines like bottom to top then?
No.
Or-
You should think of it as all executing at the same time because frankly that's what, in hardware, that's what's actually happening. There's no concept of like executing lines in a digital circuit.
I see.
It's just synthesizing into a bunch of gates and registers that kind of just pass electricity around. Yeah.
Sorry, can you quickly re-explain how in the left, like bottom circuit, B gets assigned A and A gets assigned in? Is that just?
Well, that was kind of an oversimplification. It's really just undesirable and undefined behavior. But yeah, if you use a blocking assignment, you expect that in will get assigned to A, and then after that, A gets assigned to B. So after that value is updated, the new value is used for A to assign to B.
Yeah.
And then the new value of B is used to assign to C.
Oh, yeah,
which
no,
means in just gets passed around all the way to C on every single clock edge.
No, that part I understood. I was asking about the circuit below it, like bottom left. Yeah, like how exactly
A and
the
B
bottom
are
left work.
outputs here. That should have been more clear. But in is basically getting assigned to A, to B, and then also being passed into the flip-flop and then being outputted as C.
I see.
Gabriella.
So just to clarify, in the right one,
A, B, and C are
you
outputs.
overwrite A, but then B is taking the old value of A.
Yes.
Okay, yeah.
Because if you think about it, this flip-flop gets clocked and N gets assigned to it, but at the same time, this flip-flop gets clocked and the value of A at that point is still the old value of A from here. So, it you can think of it as happening at the same time in hardware because it's how it is, but in reality, it's just going to read the previous value from before that clock cycle. Sorry.
Wait, so in the blocking assignments, why are like A and B set like to the input and C gets set to the output? Where is that? Like?
Well, because the expected behavior from doing this blocking assignment is that in gets set to A, and since it's a blocking assignment, all the other things in the always block wait for this to finish happening.
Right.
So once in gets assigned to A is now taking the value of in, so that gets assigned to B. So that means in just got propagated to B, and then likewise to C.
Right.
Because
So
these are happening one after another.
Okay, yeah, I get that, but then in the diagram, like C is out, right?
Yeah.
Output. So, okay, wait, that diagram is for the blocking, right? The one
This is the diagram for the blocking, yes.
Okay.
The idea, I mean, basically, you don't really need to you don't really need to worry about the label of in, one, and out. These are just because we have a flip-flop here.
Okay.
But you should understand that A, B, and C are all taking the value of in, and there's a singular memory cell there instead of 3. Sparsh.
If we had a blocking line followed by a non-blocking line.
That is very bad, and you should never do that.
Okay.
We do not know what it does. I think there's probably some sort of wizard wearing a purple robe in like a tower somewhere that could figure out and tell you what that does, but we could not. Aritra.
Is there any reason you use the blocking assignment instead of non-blocking?
Okay.
In combinational blocks, you would.
Yeah, that makes sense.
In sequential blocks, you just always use non-blocking. It is more
But
stable
in
that
this
way.
case, would they
In
do the same?
combinational, it is convention to use blocking assignments.
Okay, even though
All right.
Okay.
what do you think?
I think we should give them like a 2-minute break before
Yeah,
we
no,
continue.
Wait, so the right one was non-blocking,
Correct.
which means sequential?
Yes.
Okay.
Non-blocking is sequential, is less than equal sign thingy. Blocking is equal, which is combinational.
So for the bottom right block diagram, when the clock goes high, does in basically like short all the way to
No, it doesn't. Because the clock, the flip-flops will update on a clock edge, which means they take the value at that one particular instant, and there's not enough time for in to go propagate all the way through. So they just get the previous value of whatever is being passed in, which is usually.
This
which
one is non-blocking?
This is non-blocking, yes.
So then B takes the value of old A,
Yes.
Yes.
and that's what we want?
Yes. Because that's stable and predictable. You can predict that after 2 clock cycles, in will end up here. You cannot predict that. You cannot predict when in will end up at C in a like a blocking assignment.
Yeah, and it's shown on the diagram on that other slide. If you do it in
This one?
blocking, yeah, it does incur delays because you're waiting for one another. So that's why we want the non-blocking all of them happen at once on the clock edge. So we know when they're happening.
Okay, sure.
How long they should take.
But, so the advantage is predictable,
Yes.
but then the disadvantage, it takes like 3 clock cycles for it to get across.
Correct, but also that's not a disadvantage. In the context of hardware, predictable matters above all else. And it's not like you're not going to introduce a performance boost by using blocking assignment, you're just going to make your circuit not work.
Okay.
Cool. Oh, Sparsh.
This is like a really basic question, but could you just go over the differences, like summarize the difference between combinational and sequential?
Yeah, sure. So basically, when you are designing a combinational circuit, you expect that at any point your output is determined entirely based on the current value of each of your inputs. In a sequential circuit, you expect that the output might be determined based on your inputs, but it could also just be determined based on the value in various memory cells that are tracking old values of inputs. So it's a little bit more complicated, because you can use like old values of your inputs, and that makes your sequential circuits a lot more powerful. Right. I think we might have to abolish the 2-minute break due to we are very we are going very long.
Okay.
Oh,
Alright. Oh, okay, there you go.
I'm sorry. Here you go.
So this was actually a question that was brought up earlier, which is we've solved the reading stability, but what about data wires? And that also matters too. So it is a common theme in physics that you tend to work with the ideal. Penguins are cylinders. Gravity is like 10, a round number. Unfortunately, we are
Assume the cow is a sphere.
that too. We are engineers, and our gates have delays. So if you want to go deeper into those gates in the domain of transistors, essentially it takes time for signals to get passed from one end of the gate to another. Usually this is so small that you don't even notice, but if you design larger and larger circuits, like we're doing in DAV, then you will start to notice. Okay, so what that means is we need a stable period before the clock edge. Remember how we're reading on the clock edge now? Well, I think Oliver, you mentioned like what happens if something happens like right at the clock edge or like right before, right after. That is a problem too, because our flip-flop need time to latch onto the value before the second latch reads it, and this is called the setup time. So what this means is you have to have this period of time before the clock edge where your data doesn't change. So the clock is able to send the read properly. Does that make sense? Okay. And we also have a value after that, and similarly it's because we need a period of stable time after the clock edge. And this is because, again, we have that propagation delay, which is if the input changes before the second latch is like fully settled down, then our output will be unstable. this is called hold time. So we have our setup time before and hold time after, which means this period of stability. Does that make sense so far? Okay. Now you might be wondering, well, what happens if that doesn't happen? And the scariest thing for any circuit happens, which is it's not stable. We don't know what happens, and I'm going to throw out a fancy word. It's non-deterministic. So this could be anything. What comes out of this read, we don't know, and therefore we're not able to properly determine the behavior of our circuit. So that's why we need to give it this allowance so that we're able to know that, okay, this data that's coming in is what we're going to receive. So we're able to work with it from there. Does that make sense? Okay. All right. Yeah, so as we said from before, this happens when the output doesn't stabilize quite quickly enough. This could happen because, we're running too many calculations and it actually takes too long, that it takes more than the clock cycle to settle things down. Therefore, we have two options. Either we give our logic more time to figure itself out, or we reduce the logic so it takes less time to settle. Does that make sense? And by giving more time, yeah, we slow down the clock, so each clock cycle has longer for our logic. Oh, well, we were going to pause here, but it may not be happening. So, but I mean, I guess if anyone has any questions so far, please ask. No? Okay, cool. Here's my favorite part. I am Missouri. Shout out to my housemate who is actually from Missouri. But we're going to learn about finite state machines. These might have been covered in M51A, but these are probably the most important concept, in my opinion, that you'll learn to describe circuits. Okay, so what is it? As a recap, or maybe this is your first time hearing about it, they are a way to depict events in a codable way. And what that means is that we are breaking down patterns of behavior into patterns, i.e. A certain someone daily routine, remember the beginning of the lecture, into states. And so now we've broken them down into blocks, and now we have one state at a time, and remember, as we said before, we need a way to transition from each state to the next. And so this is what makes it codable. We're now going from one state to another with some certain signal. Okay, so here's the one I made to describe my annoying neighbor. So you'll see that when we're starting from sleep, right? He's asleep for some time. At 10 a.m. sharp, we start playing loud music that we can hear through the walls of our dorm, all the way until 6 p.m., where it suddenly becomes eerily quiet. Is it class? Is it something else? We don't know. But what we do know is that 8 p.m. sharp, the music is back, there's loud noises, yelling, probably alcohol, all the way until 5 a.m., where we get a little bit of peace. This is only a little bit of an exaggeration, but you can see how we've broken down his routine into certain states that change based on time, which is our signal in this case.
Oh, is there a dark arrow pointing to sleep?
The arrow pointing to sleep, that actually indicates that it is the start state. It's the one we start at. So I think I break it down here. Yeah, so these are the states that I've defined, the behaviors. Sleeping, music, maybe class, and then partying. And here are the transitions, which is time becomes this. At this certain time, something happens. And then we transition from one state to another. Remember, we're only going to be in one state at a time. And as you pointed out, yeah, we have this arrow to indicate where we start at. Honestly, I chose sleep because that's, I don't know, it's rare, but it seems like it should be a reset. So, this is my neighbor. This was my freshman year experience, guys. Okay, so what does that really mean in the context of everything we've been talking about so far? It all seems kind of disconnected, but I promise this is where it all comes together. Remember, we need memory of our current state so we know what transition we need to go to the next one. And we use registers for that, so we have some memory. Our next state will be generated with combinational logic, and we are executing these states on clock edges to make sure everything is synchronized. Finally, you notice that I've made this finite state machine time-based So we can just use a clock divider to make a time counter. Now I just need to automate calling the arrays. I wish I had done that back then. So going more technical, there's actually two kinds of finite state machines that you may or may not be dealing with. They have names and they're a little bit different, so I'll go through them right now. And the first kind is a Mealy state machine. And what it means is that the output depends on the current state and the input. So if you get a certain input while you're in a certain state, that may not necessarily mean that you change the state, but it might mean that your output changes. Therefore, because of the way we receive data, this has no lag, for one, and it might change multiple times in the same context. Versus more state machines, which I feel like we use more of, pun not intended, where output is determined by the state that you're currently in, and the output will only change when you go to a different state. So it's state-based output. And output will stay the same throughout the same clock cycle, but there is a little bit of a delay for the state to update. And yeah, as I said, you'll have to use this one more, so it might be slightly more useful for you. Does anyone have any questions so far on what finite state machines are?
Are like accepting and rejecting states relevant to these episodes?
I see 181 fellow partaker here. I guess not, because we will always be outputting something from each state. It's not necessarily, oh, this substring gets accepted and then we have that. But it's just, oh, what is our circuit doing in this state? And then how do we move states to have a different circuit behavior, that kind of thing. Okay, any other questions? Okay. And then here's just a drawing of what they look like. If you'll notice, just like this, the input changes, but the state doesn't. However, because the input's connected with an output, the output will change. Whereas in here, the slash, by the way, just means that this is the state and this is the output. And for here, this one is the input and this one's the output. Does that make sense? So you see how each of these inputs are connected with an output, but for here it's only the states. So while you're in a state, the output won't change, but only when you transition to a different one, you'll get a different output. All right, it's your time to shine from our very own president. I wasn't sure how I was going to say that. Okay, we're going to make a finite state to machine, or FSTIM for short. We are going to describe Tim in a circuit. And here's what he does. At 1:30 a.m., Tim goes to sleep. We're going to call that the sleep state. At 11 a.m., wow, I was generous. Tim wakes up and starts coding with Verilog. That's the Verilog state. At 11 p.m., Tim begins gaming. We're going to call it the game state. Now, we're going to add a little bit extra for you. When Tim is gaming and he wins, he presses the pause button, makes the pause phase for 5 seconds, and then resumes gaming. And we're going to call this state very long. And now remember, we need that initial state, and it's sleep. Okay, who wants to be our volunteer to draw FSTIM? Okay, thank you for volunteering.
When you had the arrows before, why the Mealy state machine just like the arrows have like a 0/0, where like on the right side there's only like there's no slash, just one single like value.
Oh, okay. So the reason on the Mealy is because the arrows they change on like an input in theory, right?
Oh,
The
don't worry about
arrows
the outputs, just
signify
worry
like
about
an
the states
input
and
path.
transitions.
Either
I'm limited
stays
by
the
my
same
own
state or
knowledge.
goes to a different one. And for Mealy, the
I
input
can't even.
can actually determine the output.
I think
Which is
61.
why they have the
It's third quarter.
something slash something. So the first one is the
Yeah,
input.
totally.
Like if it's in the state and the input is this, then this is the output.
You need to recall what
And
exactly
then it
we're
changes
looking at
states.
the
Or
Maybe,
states
or maybe not,
states
yeah.
and
Okay.
information from there.
Which is why it might change multiple times in the same state. Because if the input like specifies, oh, I want you to change, then it'll change. But for more, that's not the case because it's only state dependent. So the input doesn't really matter, but when an input transitions into another state, then the state will determine the next output. Does that make sense? So
what is the input
to the
and output
diagram
exactly?
input is just a signal. For example, we were using time, so it could be like a counter you have.
Okay.
And when the time hits a certain point like we had before, then it changed states. And what that just means is like, oh, the behavior of the circuit might be different.
Then in that case, what's the output?
It'd just be the behavior of the circuit.
Okay, what would the analogy be like?
Okay, so for our states, in this case, it's more. So let's say Tim goes to the sleep state. The output is he's asleep.
Okay.
And then when he's gaming, the output is he's gaming.
You were
So
missing
it's
that.
like we just named it to be more clear. Like
Oh, so the
it's
output
supposed-
only depends on the state.
Yes.
And then the state may or may not change depending on the input.
Yes.
Once
Okay.
Claire's finished answering the question, we will return.
But for Mealy, the state, the output is not like this, where we define, oh, here's the state and here's the output. But it's dependent on what state it's in and what input it gets.
Oh, okay.
So you can think
Do I have
of
to
each
worry about that?
output like a combinational circuit that whose inputs are the current input to the like entire thing and also the current state.
Okay, that makes sense.
So like the outputs are combinationally generated by both of those, as opposed to just being generated by the current state.
So we're focusing on more. So more is what we use more. Or?
You will use whatever makes sense, but you'll probably end up using more for simplicity.
Okay.
Yeah.
You'll use more.
Exactly.
Anyways, thank
Anyways.
you for drawing it.
Oliver, would you like to explain what your FSM is doing and why?
FS10.
Sure, FS10.
Okay. Basically, like chronologically written, right? We start out at sleep. At 11 a.m. it's very long time. At 11 p.m. it's game time. Yes, Binjo.
What if pog and 130 happens at the same time? Like you need to do like not pog and 130 or something?
Oh, yeah, I guess so. Everything here has to say and not pog. Or actually no. No, it doesn't matter.
Well, I mean, if Tim has a fog moment at 1:29:57, at 1:29. If Tim has a fog moment at 1:29:57 a.m. And he will return to the gaming state
Oh,
at
crap.
1:30:02 a.m.
No, you ever
And then
like
we'll-
when you game and you're like, oh wow, it's such a great win, I cannot go to sleep now.
That's what happens. But yeah, I mean, in reality, we didn't define the behavior for what happens if he is in the game, in the pogging state during the period that 1:30 passes.
Could you just say like if not pog and 130, then he goes to sleep? Would that work?
Yeah, I mean, it depends on how you want it to like actually produce your outputs. Like in this particular case, you can say if the time is greater than if the time is 1:30 a.m. or greater,
Yeah.
then you transition to the sleep state, and that
Oh.
would ensure that
Right.
you immediately go to sleep after that. But yeah, this is an option you have. There are many different ways you could go about this if you were actually making the circuit work.
Wait, so here, time is an input. Would Tim winning during the game state also be an input?
Well, we determined that pressing the pog button would be an input, and pressing the pog button would be, I don't know, the output of some other module that determines whether or not he just won.
Okay.
It's an abstract example, but FSMs are abstract in nature. Do you want to turn the screen back on?
Yep.
And we can finish
Oh
up.
yes, thank you so much.
Thank you all.
Okay.
Yo, speed run. I don't think I made it.
Okay.
But
I'll
we'll
just
do
wait
this
a little
one.
bit to go away. But yeah, here is our FS Tim. As you can see, it was pretty similar to what Oliver drew. So we have our sleep state, and yeah, we have time becomes 11 a.m. go to Verilog, and then games at 11 p.m. Pog, whenever you press the pause button, 5 seconds go back, time becomes 1:30. So it is basically what it is. Thank you so much.
Yeah. And as Adrian so cleverly identified, if the time is,
You did it
Justin,
first, yeah.
Sorry. As you guys so cleverly identified, if the time is past 1:30 when Tim returns to the game state, he will be gaming until 1:30 a.m. the next night. Anyways.
Okay, but wait. What's this? Okay, remember that we were talking about buttons and how you don't want to trigger all of that with them. How do we do that with what we learned today? How do we get Tim to press the pause button? Also, I just want to say I hope you enjoy my graphic design. Okay. So, button inputs aren't perfect. Ours are debounced, so it should be better.
Yes, but we still need to capture the edge of the button.
Yes.
Instead of just level triggering, because that has the same level triggering on a button has the same problems as level triggering on enable for a memory cell. So we tried an edge trigger, and that requires what Claire will talk about now.
Yes. So we're going to use something called a shift register. This is useful when you have a button and you still want to have that edge trigger next to them. In general, it's used to capture edges of unstable inputs. And what does that mean? It means that we have several flip-flops in this case, and we shift the value over by 1 each clock cycle, and we have input at the end. And so, I think I have it on the next slide. Yes. At the end, we'll check the value of that shift register. If it's all zeros, the button is not pressed, and that means that it's been stable for, in this case, 3 clock cycles. If it's all ones, that means that the button has been pressed for 3 clock cycles and it's stable. If you see in the middle, like there's a bunch of 1s, 0s, and all that, those we're going to call noisy, unstable values because they're not consistent. And this shift register gives us a way to ignore those and focus on the more consistent inputs. Does that make sense? Oh, and that's it.
Cool.
Oh, no.
Uh-oh. Yeah. So to quickly recap everything, today we talked about the memory cells. So how we started with latches, identified the problems with them and with level triggering, and then moved on to flip-flops, which are a lot better because they're edge triggered. And then we talked about clocks and clock dividers, which are basically what we use to synchronize our memory cells, make them predictable, and have them receive and update their values at constant intervals. And then we talked about finite state machines, which allow us to model very complex circuits using rather simple computational methods. And yeah, that's pretty much it. Thank you guys for listening.